All right, let's get started with Lesson 9, Entropy, Part 2. Now, if you recall from the first part of this lesson, we introduced to you the term spontaneous. And a spontaneous process is one that will increase the entropy of the universe. In other words, according to the second law of thermodynamics, an increase in entropy of the universe results in an increase in the randomness or disorder of the universe as a whole. So this is the criteria for a natural process to occur. If it does not increase the randomness or the disorder of the universe, it simply won't happen and it'll be non-spontaneous. So keep that in mind. Now, we did say there's an equation to actually calculate the change in entropy of the universe. And we said that it's related to the entropy change of our surroundings plus the entropy change of the system. Now, in this part 2 of the lesson, we are going to focus on the entropy change of the system. We're going to learn how to determine if it's a positive or negative sign and what the actual calculated value for the delta S of a system. So first off, we're going to look at the processes that occur in nature that actually increase the delta S of a system. In other words, increase the entropy of the system, making it positive. All right. And here are a list of different processes that you should have memorized in order to pass the exam. So you need to understand that when solids melt and form liquids, there's going to be an increase of randomness and disorder, so this would create a positive delta S. And think about that. A solid is a pretty ordered structure. The particles in the solid are tightly packed together in fixed vibrating positions. But as a solid begins to melt to form a liquid, the particles are now free. There's more degree freedom of movement that creates more randomness there, or disorder. All right, next one. A solid or liquids vaporizing to form gases. Now, gases have a lot of freedom. The particles of gases have a lot of freedom to move around. In fact, the intermolecular forces on an ideal gas is 0. So they have complete freedom, complete movement, or randomness that will occur in those particles. So a gas really increases the entropy of the system. Pure solids or liquids when they dissolve in a solvent. So usually the process of dissolving material will increase the entropy of the universe because there's more randomness that occurs, there's more particles that are distributed randomly throughout the solution. A chemical reaction that produces an increase in the number of molecules of gas is definitely going to increase the entropy. The more gas molecules or particles that you produce in a chemical reaction, the greater the entropy increase will be. When the number of moles is greater on the product side than on the reactant side, all right? More moles produced, you're going to create more randomness, all right, and less order structures. So that's what we're going to be looking for in the chemical reaction, is more moles or particles being produced on the product side than on the reactant side. All right. A substance is heated. Now, when you add heat to the system, so like you have a Bunsen burner going on and you're adding heat into that system, it's going to create more randomness because the molecules in the system are going to be free to move about more often and in a random pattern. So that creates more disorder. The more movement, the more degree of freedom of movement of particles, and the more of them, the more randomness and disorder that's going to occur. Besides, energy, an increase in energy of a system is also going to create more randomness. Energy itself is random material. It's not really material, but you can think of it in terms of the energy spreading out and randomly distributing throughout, creating disorder. The production of a gas during a chemical reaction, we kind of already hinted at that. Gas productions definitely increase the entropy of the universe. Okay, so these are processes to think about in the course of a chemical reaction. All of these processes create a positive delta S. All right, so this is what we're going to practice. We have some chemical reactions here, and let's take a look at each one of these and see if we can predict the sign of delta S. This is something you're going to have to do on the test. They're going to give you a situation like this where they give you a chemical reaction or process and say, okay, predict what the sign will be for delta S. So what I want you to do is pause this video for a moment and go through each one of these and see what you can come up with. See if you can actually predict it, and then turn it on and we'll go through the answers, okay? All right, you should have had time to go through each one of these reactions and determine the sign for delta S. All right, so I'm going to go over them with you and give you an explanation. So the first one should be a negative delta S value. Why negative? Because we're starting out with a mole of sulfur and a mole of oxygen gas, and we're only producing 1 mole of sulfur dioxide gas. So we're going from 2 moles to 1 moles. So we should see a more ordered system. Therefore, the entropy is going to decrease, all right, and be a negative sign. Look at B. B should also be negative, because you're going from, again, 2 moles of oxygen gas on the reactant side and producing essentially 1 mole of gas on the product side. So therefore, it should be a decrease in entropy. C should be a positive delta S. We're going from a solid to forming 2 gases. That should definitely increase. Plus the number of particles are increasing. We have 2 moles plus another mole that were created here. That's 3 moles of gas on the product side. We only have 1 mole on the reactant side. So we have a double whammy there. We're creating more particles on the product side, plus we're creating gases. D, all right, should be a positive delta S due to the fact that we're creating a gas on the product side. All right. E, looking at that, we should also be a positive delta S. We're creating a gas, and we also are creating more particles at the same time again, because we have 2 moles there plus another mole. That gives us 3 moles on the product side and only 2 moles on the reactant side. Okay, F, the delta S should be negative. We're creating a solid. A solid is a very ordered structure. Whenever a solid is made, it's going to increase the order of the system, and therefore the entropy should go down. Should be a negative sign. Besides, we have a mole of calcium ions and a mole of carbonate ions, and so that's 2 moles on this side and only 1 mole of calcium carbonate produced. So definitely a negative. G, looking at this, you're probably looking at a negative as well, due to the fact that we have a gas and we're changing that gas or losing the gas state to a more ordered liquid water state. Liquids are way more ordered than gases are. All right, so that's something to continue with. However, we do have 3 moles on this side, the 2 and the 3, and we only have 2 moles. We have 3 moles and 2 moles. So that might offset. But the gas is a big one, because when we lose the gas to a liquid or a solid, that's going to significantly drop the entropy. All right, so overall, I would say it's a negative. All right, next one we have here, I would definitely go with a positive entropy, because we have 1 mole of gas here versus the 2 moles of gas. So we're increasing the number of particles. I would say the delta S is probably going to be unchanged. Why do I say that? Well, we're keeping gases. We have 2 moles on this side of gas. We have a mole there and a mole there, but we're also producing 2 moles. So we're not really changing the states, and we're not really producing any more particles. So therefore, I would assume that delta S is going to pretty much stay the same sign. To be for sure, we would actually have to calculate the value, which I'm going to show you how to do in a bit. Okay, the next one, obvious delta S is negative. We're creating a very ordered structure with the solid state. We're losing gases. Besides, we have 2 moles of gas on this side versus only 1 mole. Definitely negative. Okay. K. Again, I would probably lean towards saying that delta S is positive, just on the fact that we have 3 moles of gas on this side and 2 moles of gas. So we're actually, oh, sorry, not, I meant negative. Because we're losing a mole of gas on the product side, I would say it's probably slightly negative. All right. All right. So let's go to the next one. We have probably looking at this, the delta S is probably going to be unchanged. Why do I say that? We have gases on both sides. We have 3 moles of gases on both sides. We're not really seeing a whole lot of difference here. The only way to really determine if it's unchanging or what the value is to calculate it. And so it's hard to predict it in this case. All right. M, I would have to say that delta S is positive. Again, we're creating an extra gas. We're going from a liquid to a gas state. We do have 5 moles on this side, when we have 6 moles of gas on this side. So I would have to say it's definitely positive. And then N, we're going to say negative right away because of the solid formation. And we're losing moles. We have 5 moles of particles on this side versus only 2 moles of particles. So I'm going to have to say it's definitely a negative entropy. All right. So hopefully you did really well on this. If you have questions, please write them down, and then you can ask those questions in class that you might have. But I hope this gets you started in understanding how to begin to predict the sign of delta S entropy, which you're definitely going to have to be doing this on the test. Okay. All right. So now that we have learned how to predict the sign, how do we actually calculate the delta S value or the entropy change for a chemical reaction? So it turns out that we have an equation here. It's a very simple equation that we can use to find the change in entropy of any reaction. And essentially what we need to use is what are called standard enthalpy change values. And we can find these entropy change values in a table that they will provide for you on the test, or within the problem itself, they will provide you with these standard enthalpy change values, which we'll talk about in a minute. But essentially the idea is to find the entropy change of a reaction at standard conditions. There's the not. You're going to take the sum of the standard enthalpy changes of the products, and you're going to subtract it from the sum of the standard enthalpy changes of the reactants. All right. Well, where do we get those standard enthalpy changes for this equation? From a table that looks like this. Now, your test might not exactly have a nice organized table that's really big like this. Instead, they might have a smaller table with values of entropy values in it. And you just have to look up the substance, the reactant of the product, and match it up with its entropy value, the standard enthalpy change value, which for hydrogen in this case is plus 130.6. And you just plug these values into the equation that we just looked at and solve for the delta S naught of the reaction. All right. By the way, the entropy values, the units are joules per mole Kelvin. All temperature units need to be in Kelvin when we do stoichiometry with entropies. So in other words, the units, you might want to write these down. Delta S units are equal to joules per mole Kelvin. And again, you're going to have to use the absolute temperature scale when you're dealing with entropy or enthalpy changes in general, okay? So delta H, remember, delta H is units. At standard is kilojoules per mole. No temperature units, but with delta S, you have to deal with joules versus the kilojoules, okay? And we're gonna come back to that a little later because that's a significant importance in calculations later on. All right, so let's move on back to our table. What we're gonna do now is we're gonna practice using that equation that we just saw to calculate the delta S values using this table, all right? So we have a chemical reaction here, and ultimately we are asked to find the delta S naught of each one of these reactions using the values in the table. So you look at your table and see if you can find these substances, and I'm going to go along and do them with you. All right, remember we're going to take the products minus the reactants, okay? So our first product, calcium oxide, if you look at the table, it lists it as a value of 39.8. You're going to add that to carbon dioxide gas, which is 213.6. Those are our products minus our reactant. We only have one reactant, so calcium carbonate has a value of 92.9. So we do the math, and we should calculate a delta S for this reaction, which again is the system. This is for the system. Is going to be positive 160.5 joules. Remember, joules is the unit here. All right, so it's got a pretty big value, but the important thing also is the sign, okay? It's a positive sign, which tells us that the entropy of the system is going up. And when the entropy of the system is going up, that's favorable. That means things are becoming more disordered or random, and that's what we want to see for a spontaneous process. All right? Let's do another one. We'll go a little bit faster now. Okay, again, we want products minus the reactants. So we look up NH3, and I find that it's a value of 193. However, we got 2 moles of it, so we need to multiply it by 2. All right, that's our only product, so we're going to subtract that from our reactants. Nitrogen has a value of 191.4. We're going to add that to our hydrogen, and there are 3 moles of hydrogen, so we need to multiply that by 130.6. Find that in the table. Okay, so the delta S naught of this reaction, if we do the calculation, should be negative 197.2 joules. All right, now here the sign is negative. So what does that tell us about the entropy change for this system? Well, it shows us that the system is becoming more ordered. It's becoming more organized. And so, therefore, it's not as favorable or spontaneous as we would like. Now, we can also predict that sign. If you remember, using our predictions, we have gases on both sides, but notice the mole change. We have 4 moles of gases on the product side or reactant side versus 2 moles. All right, so we would predict that the sign would be negative, which it is. All right, so see how we can use our prediction method that we learned previously here, beginning of this lesson, to predict the sign. Okay, all right, let's do one more together. All right, again, we want to find delta S for this reaction. All right, so let's see here. We're going from 2 moles of gas to 2 moles of gas. So this is going to be hard to predict what the sign is. So really the only way to know if delta S is changing much is, and what sign it is to do the calculation. So let's go ahead and do that. So we're going to start out with 2 moles of HCl. If you look at the table, HCl has 107 joules per mole Kelvin. We only have one product. We're going to subtract that from chlorine, which is 223.0 from the table. We're going to add that to hydrogen's value, which is 130.6. Okay, now we'll do the math for the reaction, and what do we get? We get a positive 20.4 joules. Okay, so there is a change. It's not a big change as we've seen from the other ones, and we could kind of predict that the change would be pretty small because we're only producing, we're keeping the same number of moles on both sides, plus we're producing gas, keeping the gases. So not a big change, but it is positive. It is becoming more disorganized or random. So this is a favorable, spontaneous process based on our current calculations here. All right, so this is it for this part of this lesson. Basically what we've learned here is how to predict the sign, positive or negative, for the entropy change for the system, chemical reaction, and also to calculate the value using our equation delta S naught for the reaction is equal to the sum of the entropy changes of the products minus the entropy changes for the reactants. All right, so that is it for this part. Review your notes, study hard, and bring questions to class, and that is it.